Good evening, everybody. I wanted to do a second video just due to the fact that the last video I had just didn't catch all of the work that I was showing, and it was only showing partial. So I'm going to delete that one, going to replace it with this one. So wanted to go through several examples with you, and I'll upload that back in the same folder, which should be Exam 3, Week 10. So as we're looking here with this is actually a radical equation, and I've got S for our speed of the pendulum and L for the length of the pendulum, and pi is irrational, and we will stay in terms of pi on this problem, but the speed is 4 pi, and that's going to equal 2 pi times the square root of L divided by 32. Now, remember, this is in radical form, so the root is understood to be 2. And since I want to solve for L, I just want to start peeling back layers of this operation. And the operation with this happens to have multiplication involved and a square root and division. So we'll do those in the reverse order. We'll end up dividing and squaring and multiplying. So I want to solve for L, so I'm going to divide by the 2 pi. And that's going to divide out, and 4 pi divided by 2 pi is 2. And then I'm left with L divided by 32. So again, since it's a square root, remember, the radical form can be written as a rational form. So I'm going to come up here and rewrite it in that rational form, and that will be L divided by 32 raised to the 1/2 power. Well, I want to solve for L, which means I've got to create this power to be 1. So to do that, I'm going to square both sides of this equation. So 2 to the second gives me 4. And remember from our exponent rules, with rational exponents, the power to power rule allows you to multiply. So if I take half of 2, or 2 times 1/2, I get 1. So I get L divided by 32. So now I see division, and so I want to multiply both sides by 32. And this divides out, and I'm left with L equals 4 times 30 is 128 feet for my length. We'll talk some more about radical equations in our upcoming meetings. So, got 3 examples here where we're just simplifying the radical. And remember from class last week, we talked about what we're looking for is one of the factors to be a perfect square. And if we can get to one of them being a perfect square, the other one could be a prime number or a composite number. So the square root of 24, we've got multiple factors, but 4 and 6 will work because the square root of 4 is 2. The square root of 6, we'll leave it as the square root of 6. Even though there's other square root of 6 is, the radicand is composite, there's no other perfect square factor, so we are simplified. Square root of 24 is equivalent to 2 times the square root of 6. Square root of 512, we would say, is 256 times the square root of 2, and the square root of 2, the radicand is prime. Square root of 256 is 16, so I get 16 times the square root of 2, and this is the simplified form of the square root of 512. 224 could simplify to the square root of 16 times the square root of 14. Square root of 16 is a perfect square, and it's going to be 4. And the square root of 14, radicand of 14 is composite. It's not prime, but there's no other factors of square root of 14 that would be a perfect square. So here would be our factored forms, simplified forms of the radical. Let's take another one. Let's look at the square root of 153. and that will be the square root of 9 and the square root of 17. I cannot simplify the square root of 17. Square root of 9 becomes 3, so I get 3 times the square root of 17. 150. Notice it ends in 0. So 15 and 10 are factors, but neither one of those are perfect squares. So 25 and 6. So the square root of 6 and the square root of 25 would be factors of the square root of 50. This would be a perfect square. Square root of 25 becomes 5. Square root of 6 does not simplify. And then the square root of 252 would simplify. The square root of 36 times the square root of 7. Square root of 36 would be 6 times the square root of 7. So again, simplifying radicals, and what we're looking for is one of the factors to be a perfect square, and the other factor to be a prime number or a composite that cannot be simplified anymore. So we're searching for our largest perfect square factor. All right, so jumping into complex and imaginary numbers, we kind of discussed this the other day in class as well. If I have x squared plus 1 equals 0 and I wanted to solve for x, that would give me x squared is equal to -1. And if I solve for x, I'm going to take the square root of both sides, similar to our pendulum problem with the length and solving for the length. This would give me x is equal to square root of -1. And since square root of -1, we would be an imaginary number, this leads us to what I would represent. I would equal the square root of -1. And we will use that in the subsequent problems where we have a negative under the radical. So we'll utilize the imaginary number I. And then remember, if I want to square both sides, that would give me what I squared would be, which would be -1. So I is equal to the square root of -1. I squared is equal to -1. So let's take the square root of -81. Since we see the negative under the radical, we know that that will become I times the square root of 81, and the square root of 81 would be 9. We're going to look at just the positive side of this, and we get 9i. Again, you recognize you've got the square root of -56. And square root of 56 divided by, we're going to have I times the square root of 56, which would then become square root of 4 times the square root of 14. We're going to keep bringing our I down. So square root of 4 becomes 2, so I get 2i times the square root of 14. So again, very similar to the previous two screens we were looking at with problems where we're simplifying. We're looking for perfect square factors, except the difference is here is I've got a negative under the radical, and that negative becomes I. I'll look at another one where I've got a coefficient factor 2, and I see this the negative under the radical, so I know that's going to become I, and now I'm looking at the square root of 125, and that's going to be square root of 25 and the square root of 5, all multiplied by 2i, so the square root of 25 becomes 5, so I've got 5 times 2 times I times the square root of 5, and all this was simplified to be 10i times the square root of 5. With this one, again, we recognize a negative under the radical, so negative square root of 3 times I, and then square root of 180 And if I factor that, I'm going to get the square root of 36 times the square root of 5. And I've got negative 3i multiplied by all of that. Square root of 36 is my perfect square, so that's going to become 9 times negative 3i. Simplify it all, I get negative 27i times the square root of 5. And that would be your simplified form of negative 3 times the square root of negative 180. All right, now switching gears, looking at the next two slides dealing with adding and subtracting, or the next three slides, I believe, working with adding and subtracting radicands. Very similar to adding and subtracting fractions, where you would like to see common denominators. And we know that if we have common denominators, we're allowed to add. So 1/2 plus 3/2 would be 4/2, which we say would be 2. And the reason we can add those together is because our denominators are the same. Same idea here. So with part A, I've got 5 times the square root of 10 minus 11 times the square root of 10. So I know I'm working with the square root of 10. So I'm looking at the factors outside. So I've got 5 minus 11, and that's going to give me negative 6 times the square root of 10. You're always thinking, can you simplify? And the square root of 10 does not have any factors where one's perfect, so we will leave it. And then number 2, or part B, both have radicands of 15. So then our i's go out here to negative 9 and a positive 15. So negative 9 plus 15 would be positive 6 times the square root of 15. And I cannot simplify square root of 15. So part C, I see I've got 3 times the square root of 6 minus 4 times the square root of 6, and the radicands are the same. So what's 3 take away 4? And that would be negative 1 times the square root of 6, or just negative square root of 6. Either one's fine. And then finally, part D, I've got 3 times the square root of 3 minus 5 times the square root of 27. Well, you just don't want to give up with it. You want to try to factor. You certainly can't say 3 take away 27. Need to have the same radicand. So you're going to look to simplify the square root of 27. That's going to be the square root of 3 and the square root of 9. And then continue to simplify. So 3 times the square root of 3 minus 5 times 3 times the square root of 3. So this will be 3 times the square root of 3 minus 15 times the square root of 3. Radicands are the same, so what's 3 take away 15? We get negative 12 times the square root of 3. So that's the big key with this is, well, what happens if the radicands are not the same? Then you want to simplify and hope that you can get it down to where they have the same radicands. Sometimes you can't, and then you would leave it as if you can simplify here, but sometimes if you had square root of 3 minus the square root of 5, then you would leave it as is. We'll go to the next screen and we'll look at the next problem. I've got 2 times the square root of 45 minus 2 times the square root of 5. Radicands are not the same. So since this one's already simplified as much as you can always try to think, will the square root of 5 be a factor? And in this case, it is. Square root of 9 times the square root of 5. So the square root of 9 becomes 3. And so that would be 6 times the square root of 5 minus 2 times the square root of 5. Radicands are the same. So what's 6 take away 2? You get 4 times the square root of 5. Again, the radicands were not the same, so we want to try to simplify and hope that they do become the same. So part B is 3 times the square root of 18 plus 3 times the square root of 12 plus 2 times the square root of 27. All three are the same. Well, you can't stop. You can't add 18 and 20 and say that's 30, and 30 plus 27 is 57 and say the square root of 57. Can't do that. So you want to try to simplify and look for perfect square factors, which these are simplifying that way. So 3 times the square root of 9, which would be 3 times 3 times the square root of 2, plus 3 times the square root of 4, which would be 3 times 2 times the square root of 3, plus 2 times the square root of 9, which would be 2 times 3 times the square root of 3. So this will be 9 times the square root of 2, plus 6 times the square root of 3, plus 6 times the square root of 3. And these are my like terms. They have the same radicand. So what's 6 plus 6? We get 12 times the square root of 3. And we were adding that on to our other piece. Cannot add these. Square root of 2, square root of 3. Can't say that it's 21 times the square root of 5. Can't do that. Radicands are the same, so you leave it. So there's some practice there of seeing what happens when you're adding or subtracting radicands, when the adding and subtracting radicals when the radicands are different. What your thought process is that you want to try to simplify as much as you can, hoping that you may find some common radicands where you then add the coefficient factor to the left of the radical in order to simplify. So I hope this has been helpful. We'll talk more next week. Definitely check the upload the quiz that I'll attach, and so take that. Use this video to help you answer. So, hope this was helpful. Y'all have a great night.